Hi, welcome back to Statistics 1. We're up to Lecture 13. And if you've made it this far, I'm willing to bet that you'll make it through the entire course. Because that last topic that we covered, multiple regression, mediation, moderation, that was the toughest material that we'll cover in the entire course. In fact, you'll see this lecture is actually amazingly simple in comparison to what we just did. So if you made it through that last week, great. This next week, you can take it easy. It's much easier. So today we're going to talk about t-tests, the simplest tests in statistics. And in this lecture, there's just two segments. In the first segment, I'll give you an overview of t-tests, the different kinds. And then in the second segment, I'll give you specific examples of dependent and independent t-tests. So in terms of overview, as I just said, this is an odd progression. We just did really complicated analyses in multiple regression, right? We were doing moderation analyses with centering predictors and using dummy coding and creating interaction terms, all sorts of stuff. So this is an unusual progression in a statistics course, and I actually don't know of any other professor who takes this approach. I don't know of any textbook that takes this approach. So why do I do this? Well, I do it on purpose for a very explicit reason. And that's to drive home and reiterate that lesson from the first lecture is nothing beats a simple, elegant, controlled experiment where there's just one manipulation and one dependent variable, and you can make a really nice, strong claim about causality. That's great. Nothing beats that. Think back to some of the examples we were dealing with in multiple regression. They got extremely complicated really fast, right? So just think back to some of the multiple regression examples we dealt with. We had to go through all the matrix algebra to come up with estimates of regression coefficients. And there was mediation, moderation, centering, dummy coding, lots of stuff. And then at the end, when we interpreted the results, there were all these qualifications on the arguments that we can make. Right? That's not the case for a simple controlled experiment, right? So think back to just simple regression. We did all this work, and then we came to this final conclusion that the slope for some predictor x is b, and then you said, wait, if I do a multiple regression and I add in another predictor, then it's not b anymore. It changes once I add in another variable. So there's qualifications on the interpretation of the results. Again, with mediation, we had two variables, x and y. They're correlated. We found a variable m, the mediator, that say it fully mediated that relationship. But then somebody said, well, you still can't really make a strong argument because correlation doesn't imply causation. So you might have shown statistical mediation, but you don't have true mediation. You're not really getting a causal mechanism. So again, qualification on the final interpretation. Same thing with moderation, right? We saw that, hey, x and y have a nice strong positive correlation, but wait, add a moderator and it might go away. So there are a lot of sort of qualifications and disclaimers that we needed to put in at the end of every example. And that's because we weren't working with examples where we had randomized controlled experiments. So let's take a step back from those messy designs and just go back into like lecture 1, like the polio vaccine study, just simple, elegant experiments. In a simple experiment, you just have one independent variable, one dependent variable. So that's, again, why I started with the polio vaccine studies. Just perfect example. So independent variable, half the people are randomly assigned to get the vaccine, half are randomly assigned to get a placebo. Dependent variable, if we're looking at the level of the individual child, is just were they diagnosed with polio or not? If we're looking at groups, then we can just look at rate of polio in a group. The way to do a statistical test on that, I avoided the statistical test part in lecture 1 because I didn't want to get into the math and significance testing and all the stuff that we've covered since. But the statistical test is real easy. It's a t-test. T-tests just compare two means. So that's it. That's what it. Compared to multiple regression, this lecture is a breeze. So we're just going to compare two means. And we use a t-test to do that. There are variations on that. So there's actually a z-test before we get into t-tests. And in this lecture, we're going to just cover 4 variations. So z-test, a single sample t, a dependent t, and an independent t. You'll see they're very slight variations on one another, and all of them just compare two means. Very easy. Just a historical side note, which is sort of fun. Why is it called students' t-tests? A lot of students don't actually know this. And it's a really interesting tidbit because it was developed by William Gossett in 1908. And for the purpose of monitoring the quality of stout beer at the Guinness Brewery in Dublin, Ireland. I can't think of a better reason to do statistics. I love Guinness. But the management at Guinness, they considered their whole process a secret, including the statistical analysis behind monitoring the quality of stout. So they convinced Gossett to publish under a pen name, and he just used the name student. So it became known as students' t-test. But it's really Gossett's t-test. Or if you want, you can just create a drinking game here, and every time we do a t-test, you have to drink a Guinness. I think that's the way to learn stats. So back to the Z and T. I'm pitching this whole lecture as t-tests, but first I want to say we should start with the z-test. And a z-test, you'll notice the formula is just like the formula for a z-score, except now we're at the level of means instead of the level of individuals. So a z-test is conducted to compare an observed mean, like a sample mean, to an expected mean, like a population mean. And we use the z-test when we know population parameters. So that's actually rare. We don't usually know population parameters. That's why we engage in a lot of inferential statistics, because we're getting sample data to make inferences about populations. But if we do know a population mean and a population standard deviation, then we can use a z-test. So an example of this is, I've been using throughout this course the example of the SAT test in the United States as a college admissions test. That's a situation where we actually can get our hands on the population parameters because the people who develop the test, they get all the data back, and they have the mean for everyone who took the SAT in a certain year. So for example, if I wanted to compare my students at Princeton, that sample, if I wanted to compare their mean SAT to the population, I could do it with a z-test because I could get the population mean and the population standard deviation from the College Board. They're the people who developed the SAT. But it's more common that we don't know those population parameters. So we might do a t-test. And again, we could do a single sample, dependent t, or independent t. And I'll walk through each of those. Before I advance the slide, though, keep in mind all of them are just a ratio. And this is true of all significance tests that we'll be using in this class. They're just a ratio of sort of what you observed in the numerator relative to what you would expect due to chance in the denominator. And if what you observed is like 2 or 3 or 4 times greater than what you expected just due to chance, then you can say you found something significant. But if the ratio is 1 to 1, then you really haven't found anything. You've just found what you would expect due to chance. So when to use each of these tests? Again, we're going to cover 4 different tests in this lecture. I've already sort of talked about the first 2. So use a z-test when you know the population mean, you know the population standard deviation, and you want to compare a sample mean to a population mean. It's rare that we do this, but it's a good place to start. It's real easy. Single sample t is exactly like that, except you don't know the population standard deviation, which is more likely. And then the more common tests are dependent t and independent t. And a dependent t, you're comparing the same people in just two different conditions. So I started out with one of the experiments that I started out with in lecture 1 was the working memory training experiment. So suppose I wanted to compare people's working memory or their intelligence score pre and post training. So I have two means, before and after training. It's the same people, so they're dependent. I would use a dependent t to compare those two means. Independent samples t is just I have two different groups. So there, if I wanted to compare the training group to the control group, those were different people. Or if I wanted to compare men versus women, that would be an independent samples t. The groups are independent. The only slightly difficult part of this lecture, and I think this content, and again, I'm speaking from experience teaching this material a lot over many years at the undergraduate level, is there's just a lot of notation to keep track of. So just be aware of that. Don't make silly mistakes on using the wrong formula for standard deviation or standard error. You'll see there's a lot of the notation looks similar, so just be careful. So I've created this table, and in the next slide a list. So maybe keep these handy if you're new to this, just to avoid, again, those typos or silly mistakes. So again, the general formula is observed minus expected over standard error, but the actual calculations change depending on what kind of design you have. So in a z-test, you're comparing a sample mean to a population mean, and you're getting standard error for a mean. In the single sample t, same deal. But when you go to dependent and independent t, you are observing a difference. You're observing the difference between either two conditions in dependent or two groups in independent. So you're getting what's called a standard error for a difference. And the calculation of that is slightly different than standard error for a mean. But conceptually, it's all the same. It's just what did you observe relative to what do you expect due to chance. Okay, and again, here's the list just to, again, help you avoid making silly mistakes or typos or confusing some of these concepts. Remember that I use the Greek symbols for population parameters. So sigma is the population standard deviation. Mu is the population mean. SD is sample standard deviation. M sample mean. This goes back all the way to lecture 2 on descriptive statistics. I'll use SE for standard error generally. But I'm going to use this notation to make distinctions about what kind of standard error I'm calculating. So SE sub M, standard error for a mean. SE sub MD, standard error for a difference, but a mean of different scores. And I'll show you that in the dependent case. And then standard error of a difference is the standard error of the difference between two groups. So these last two are slightly different, and you'll see that in the next segment. Remember, when we do this null hypothesis significance testing, we calculate the t value or z value, and then we get a corresponding p value. And if we set alpha to 0.05, then if our p value is less than that, then we reject the null hypothesis, and we say, hey, we have a statistically significant effect. And in these cases where we're comparing two means, we're just saying these two means are significantly different. So where does the p-value come from? Remember, the logic of the p-value and where it comes from is all based in the central limit theorem. So if that's sort of fading in your memory, go back and review the logic of central limit theorem. But it just depends on basically sample size and whether or not you're doing a directional or non-directional test. So just to refresh your memory about the central limit theorem, Remember, we assumed that probability histogram or distribution of sample means was the phrase I used. Remember, the idea behind that was we go into this game of null hypothesis significance testing assuming that there's no difference between our groups or between our conditions. And then we observe some outcome, and then we calculate the probability of that outcome given the assumption that the null is true. So again, remember, if the null is true, then we should expect a mean difference of 0. We should see no difference between the two groups we're comparing or the two conditions we're comparing. But remember, going back to the lectures on central limit theorem and sampling, there's sampling error. So if I'm sampling two groups or I'm measuring people twice, those means aren't going to be perfectly equal. There's going to be sampling error. So how much sampling error do I expect? Well, that's standard error, right? And standard error is one standard deviation in this hypothetical distribution of sample means. So if you get a z-score of, say, 3, you're out here, that means your observed effect is 3 times bigger than what you would expect due to chance. That means the probability of that happening, assuming the null, is really, really low. And the way we get the p-value or calculate the probability, it's the percentage of area under the curve beyond that point. And if you look at the percentages here, beyond 3, there's not much beyond 3. So the p-value is really, really low. If you're doing a z-test, and if you're doing a non-directional z-test, then the value you need to get past significant, or to get a significant result, I should say, is 1.96. I just know that because I teach this a lot. But actually, most people who do research know that number, 1.96. That's because if you look in this distribution, here is the -2, and here is +2. So 1.96 is just below that. What that means is 2.5% of the distribution is beyond 1.96 on this end, and 2.5% of the distribution is beyond -1.96 on the lower end. That 5% represents the alpha of 0.05. That's where we get the phrase p is less than 0.05. It's statistically significant. You're so far out on the margins under the assumption that you would wind up in the middle that you raise a red flag and say, wait, something's weird. I'm going to reject the null hypothesis. Again, just like way back in the beginning of the course when I did this at the level of individuals. Remember, I used the example of measuring body temperature with the wand, and I was under the assumption that everyone in the class was healthy, and then I sampled somebody and they had a temperature of 103. And that put them like way out here. Their z-score was like, I think it was like 4 in that example. Well, that violates my assumption that everybody in the room is healthy. That person's not healthy. Their body temperature suggests that they're sick. So that's like raising a red flag, reject the null, send them to the hospital. This is the z distribution. So we know like 1.96 gets us a p-value of less than 0.05. It turns out, and this is where Gossett at the Guinness Brewery made a contribution to statistics, is it turns out that this hypothetical distribution that we estimate by calculating standard error, it changes depending on sample size. So we can assume this nice distribution if we have really large samples. Basically over 100, and you're close to this. But if your sample sizes are less than 100, then the distribution gets a little wider, as sample size drops. What that means is you need higher t-values to get p less than 0.05 to say that you have a significant result. And that should just conceptually make sense, because remember, what really drives standard error, what really drives sampling error? Sample size, right? So if you have low sample size, small sample size, then this distribution is going to get fat, which means you're going to need more than 3 to get p less than 0.05. Okay? So there's one z distribution. This is it. What Gossett published was what we call a family of t distributions. So there's one z distribution, but there's a family of t distributions. There's one for every sample size, going from a sample size of 10 up to like a sample size of 120. Once you get to about 120, you're converging on the z distribution. So then you can just assume that if you get close to 1.96, your p-value is going to be less than 0.5. So that's the distinction between z and t. So it's important that you know degrees of freedom, because degrees of freedom will tell you which t distribution in the family of t distributions you need to look at to calculate your p-value. Of course, you're not doing this. R is doing this for you, but that's the way it works. So with a z-test, you don't have to worry about degrees of freedom. You have the population parameters. Single sample t, it's just number of people in the sample minus 1. Dependent t, same thing, because you're looking at different scores. Independent t, it's the number of people in the first group minus 1 plus number of people in the second group minus 1. So let's just do one example of a single sample t, and that will wrap up this segment. In a single sample t, real easy, we're just comparing a sample mean to a population mean. So in the numerator of the formula, it's observed minus expected. So the observed is the sample mean, the expected is the population mean. And then what's standard error? Well, standard error of the mean. If you go back again to descriptive statistics, standard error of the mean is just standard deviation over the square root of n, or as I've written it here, I've made it squared. So it's standard error squared is standard deviation squared, or variance over n. Actually, I wrote it both ways. And remember, from descriptive statistics, standard deviation squared is variance, or mean squared. The way we get that is sums of squares over n minus 1, or from here on out, I'll just say sums of squares over degrees of freedom. So really easy example, just to wrap up this segment. Suppose it takes rats just 2 trials to learn how to navigate a maze to receive a food reward. Suppose we know this. It's a really simple maze. They learn it after just doing it twice. Suppose the researcher surgically lesions a part of the brain that we think is important for this type of learning, and then they look at this experimental group to see, how many trials does it take this experimental group. And I made this really simple so we could just do this quickly, and you'll see the math is very simple. You did basically the same calculations in descriptive statistics. So let's suppose we just have 5 rats. If you were really doing this, you'd want to have more than that. And these are the rats that are lesioned, and this is how many trials it takes them to learn. So you can see it's taking them more than 2. They're not learning it right away like healthy rats. So what we need to do is calculate sums of squares so that we can get mean squares, so that we can get standard error. So what I did is I got the mean, and then I got deviation scores. I square the deviation scores, sum them, that's sums of squares. So variance is sums of squares over degrees of freedom. Sums of squares from the previous slide was 26. There were only 5 rats, so degrees of freedom is 4. That gives me a variance of 6.5, which leads to standard error of 1.14. 1.14 is, let's pause on that number, that's how much variance I would expect just due to chance. Right? It's just sampling error. So yeah, we know that for all healthy rats, it's like 2 trials, but maybe the rat gets lucky and gets it on the first trial, or maybe one just screws up and gets it on the 3rd trial. So we might expect maybe 1 trial deviation by chance. So we need to demonstrate something more than 1 to see that this lesion made a difference. What did we observe? Well, we observed a mean difference, or a mean of 6 trials. So that's a lot higher than 2, and 6 over 2 divided by 1.14 gives me a t-value of 3.51. Again, think about that distribution. You're way out in the tail. So what's the p-value? It's 0.012. The probability of observing this outcome, assuming the null, is very low. It's 0.01. So we reject the null hypothesis, and we can say that this is a significant result. Remember, though, that null hypothesis significance tests are biased by n. So it's always good practice to supplement that result or that information with an estimate of effect size. And the way we're going to do effect size in t-tests is Cohen's d. And it looks just like the t-test formula, but instead of dividing by standard error, we're dividing by standard deviation. What that does is it eliminates the bias by n, right? Because in standard error, in the denominator is n. So if you drive that up, standard error goes down. We've covered that. That's not true of standard deviation. That's not biased by n. So this just tells us how much did we shift this sample mean in terms of standard deviations. And we get a Cohen's d of 1.57 in this case. That's a big effect size. Really, anything over 1 is a big effect size. But judging what's large and what's small in effect size is a bit subjective, but everyone would agree that 1.5 is large. So strong effect. But again, the point is, whenever we do this mean comparison, we want to report the t-value, the p-value, say whether it's statistically significant or not, and then supplement that with an estimate of effect size because of all the problems associated with NHSTs.